Hello, can you hear me now? Okay, great. Thanks. So we'll discuss on those topics. So first, let us see what is basis. We have already seen that a topology on a set X, it is a subset of power set. It contains some elements. So it has some property, that is, for X belongs to X, there exists an element U which contains X and contain in this. Sorry. So for all X belongs to X, there exist U contained in tau. This is one property. Another property is arbitrary union and finite intersection. So topology tau is closed under arbitrary union and finite intersection. And for finite intersection, this is equivalent to having closed under intersection of two open set. So those elements U, those are actually called open set. Now the thing is that topology on can we define topology on arbitrary set? So it is difficult, because we have already seen that for if there is only two element, then there can be there are many possibility of a topology. So what are the possibility? For example, one topology is phi and the whole set X, and another possibility will be take everything, the whole power set. So those are and there are also two other possibility: phi take the whole set and A, and similarly the another one where B is the only non-trivial element. So there are four elements, but if the size of the set is greater than 2, then there will be lots of choices. So in general, for an infinite set, it is hard to describe topology by explicitly mentioning all those elements. So one easier way to construct a topology on a given set is by in terms of basis. So let us define basis. So a basis for X, it is a collection of subset of X. Collection of subsets of X such that it has two property. One, for all X belongs to X, there exist, so sorry, that is actually wrong. This is not what I should mention. Empty and X, those two belongs to tau. So for all X belongs to X, there exists an element. So let me denote the basis by script B. there exists an element B belongs to B such that X belongs to B. So that means for example in real number, we have seen that for real number the those forms a basis, that is that satisfy the first property. Take any real number, there exists an open interval like a comma b which contains that element. And similarly for Rn or R2, whatever we see for R2, if we take this open ball, that is b, suppose this is the point x, b x comma some radius r, then this satisfies, if we take all those collections, then this will also satisfy this property. That is, for all x belongs to x, there exists an element like this which contains that point. So this is first property, and the second property is if b1 and b2 two element from the basis, and then there exists b3 such that, and also we are assuming that x belongs to b1 intersection b2, then there exists b3 such that x belongs to b3 and b3 also containing b1 intersection b2. So here we can see, if we take intersection of, suppose this x containing those two open set, then we can see that we can found a smaller open set inside this intersection. Similarly for the first one, that is here if we take AB and if we take another interval, suppose CD is another interval, then the intersection itself, that is the intersection itself is another interval, right? So the new interval is, so this is C comma D, then C comma B satisfies this property. So take B3 as C comma B. Therefore, if we take intersection of two element of the basis, then there exists another basis element which will contain in this intersection and which satisfies this property. That is, take any element, then we can choose another element such that this property holds. So those are properties of basis. So this is the defining properties. Now the important thing is that we can generate a topology using this basis. So let me define topology tau generated by basis. Script B. So what is topology generated by a basis? So we define U. U is said to be open that is, it is equivalent to saying U belongs to T, right? If there exists, so if for all x belongs to U, there exists a basis element B belongs to script B such that x belongs to B containing U. So in this case, so those U forms a topology. So we are taking those U. So it is, this definition might be confusing, but it says we are taking all those U such that for all x belongs to U, there exist an element B which satisfies this property. Okay, so we are taking all such U. Then, so these collections form a topology. That's why it is called topology generated by this script B. So let me give an example. Can you provide a non-example to show why second condition is needed? Second condition means what is the second condition here? Okay. So second condition says that for intersection B1 intersection B2, because the thing is that this should be closed under intersection. That is the property. If we do not take the second condition, then that will create a problem actually. That is, you need to prove that tau generated by this forms a topology. To prove this, you need to use this second condition. That is, you need to prove that it is closed under finite intersection. So that's why that condition must be taken. Otherwise, it will not form a topology. Okay. So the most useful example is metric space. Metric space is defined by a basis. So we define some distance. Metric space means X with a distance D, right? So first we need a topology or a basis. Okay. The thing is that usually we define a topology in terms of a basis because it is easier to define. Otherwise, for an infinite set, it is hard to, that is explicitly mentioning all those elements of the power set which forms a topology. So it is like vector space, right? In vector space, how do you see a vector space? For one dimensional vector space means you can define it in terms of the scalar 1. That is, just multiply this scalar to, that is, extend this scalar to all those directions. Now you can create the real number, whole real number. That is, it is easy to mention, easy to define vector space in terms of basis. That is, the whole thing is depending on those two dimensions. Okay. Yes. First, we need a vector space. You can define in terms of basis also. That is, take any three element, for example, E1, E2, E3. Then you can define a vector space spanned by this element. Right. So those three elements generate something which is a vector space. We can prove that. That will form a vector space. That is, all those properties closed under addition, closed under scalar multiplication, those will be satisfied. So similar kind of a situation is that. That is, we are taking some element which satisfies some certain criteria. Then we can create something, and that will be a topology. So it is like this. So here we don't need any extra property, but in topological space, it's we need certain properties. Otherwise, it will not be a topology. So an example will be metric space. So what is metric space? We can define open ball B x comma D, small x comma some r, is defined by all those elements. Maybe let us define in this way. So take all x such that distance between x and a is strictly less than r. Then this b a comma r forms a topology. So we need to check why this is a basis. Why this? If we take this b a comma r, and vary those A belongs to X and R is real number, maybe we take positive real number, otherwise there will be a problem. So this forms a basis. How do we see that this is a basis? Because for R2 it is very easy to see. In general, it will be means there need to be done some analysis. Yes, what is the confusion? Uh, so the definition again. Yes, here also we first define topological space, but we are giving a way to create a topological space. We are describing a way because in general it is hard to construct a topological space. Means arbitrary topological space. Okay. So metric space. So for R2 it is easy to see. That is, if you take first property is easy because if you take any element A from this X, just take this open ball B A comma 1 you can take. But the second property you need to check. That is, for two open balls, suppose first one is B A comma R1 or R, and the second one is B A comma R dash, A dash comma R dash, then you need to prove there exists another open ball contained in the intersection. So you can prove this fact, and using that you can create a topological space by this metric. That is, this is the basis for the topological space. Okay. So those are few things, and okay, let me explicitly mention an example. Suppose consider this space X containing three elements A, B, C, and tau is empty set X, and it has A and another thing AB. So can you give me a basis for this topological space? Yes, tau itself will be a basis because it satisfies all those property. But you can also give me a non-trivial basis other than tau. So we can discard empty because the property will be trivially satisfied. So you can only take A and AB, right? No, A and AB is not. You cannot take A and AB because then C, there is nothing containing C. So you can only discard empty set in this case. Okay, but let me create something non-trivial. AB, BC, and so in here we are taking B. Okay. Now can we give an example of basis? So just take this B, AB, and BC. Okay. So see that if you take, so for all take an element A, there exists an element AB which contains this A. Similarly, take B, you can see there is B, or take C, there exists an element, that is, there exists a set inside this script B which containing this C. So this satisfies the first property, and the second property is we need to check intersection. So intersection of these two elements, it will be B. right? So intersection of AB, BC, it is B. But we see that, so there is only one possibility, that is only B belongs to this intersection. And we can see there exists B which contain in that. So this property is satisfied, right? Take any element from the intersection, there exists one element from this group. So this forms a basis.
Sure. Sir.
Okay.
Sir.
Now the interesting thing is that
Hello.
the topology
Hello.
generated by discrete P, it is actually the collection of all all union of the element from script. Collection of all union from discrete P. So note that, so it is the process to create tau from this given script P. So here we can see that, okay, so here we can see tau script B we can create. So take any arbitrary union of all those elements. So take union of those two things, you will get script B, right? So if we take the empty union, this is empty set, that is trivial. And if we take union of those two things, we will get, so if we only take union of those single thing, that is we will get B, AB and BC. And there is another possibility which is union of those two things, which is ABC. So we'll get the same tau. So that is the thing, that is the topology is generated by script V. It is the collection of all union of elements of script V. So what is the question? Sir, what does? So empty union means, so union is taken over some index. There, the index set, I am taking this as an empty set. So there is nothing. Okay. So we are not taking any union. Okay, it is like zero. There is nothing, no union. That's why it will be empty. Now, suppose a topology is given. Now, the question is, can you extract a basis? Or say whether something is basis or not. So one way is like this. So C, suppose C be the collection of all open set. So collection of open sets. Open set means elements from tau. Okay, elements from tau, such that for all u belongs to tau, there exists C belongs to C, such that X belongs to C belongs to U. Then this script C form a basis for tau. Okay. So how do we check something is a basis or not? So for for every open set in tau, there should be some element from this script C which satisfy this property. Okay, sorry. For all x, for all u belongs to tau, and there is another condition for all x belongs to u. So if this criteria holds, then C forms a basis. Okay. And there is a comparison. So we previously seen if tau is contained in tau dash, then tau is said to be a coarser topology, and tau dash is said to be a finer topology. So it is tau dash is finer than tau, and tau is coarser than tau dash. Now, suppose basis for those two topology is given. So let B and B dash, those two are basis for tau and tau dash respectively. Now, can we compare in terms of basis? So the answer is yes, we can compare in terms of basis. Okay. So tau dash is finer, that means for all B belongs to this script B and X belongs to B, there exists an element B dash from this script B dash such that X belongs to this B dash containing
Hello.
B.
Hello.
Then tau dash will be finer.
Sir.
That actually this actually means that take any element
Hello.
from B dash, uh, take any element from this B. B belongs to this tau. That is also an open set of tau dash. So open set of tau dash means exactly that. That is, B is open set of tau dash means there should be an element, basis element, such that X belongs to that basis element and B dash containing. No, Sandeep, you are not audible. Sorry. So this is how we can check if something is finer or not. This makes the checking process easier. Otherwise, direct checking is always not possible because there are infinitely many sets and we can't handle those things. Okay. So those are few things, and now there is a way to create basis. Sorry, I can't. Yeah.
Hello.
So subbasis. The question is, uh, can we create a topology? So suppose X is a set, and we are taking some subset from this X. Okay, we are taking subsets of X. Now the question is, will it form a topology with intersection and union? So that is partially true. So if this satisfies some property, that is because for basis we need for any element from this X, there should be an element which contains that X. That is, for X belongs to X, there exists U. Yes, there may be some problem. So there exists U which contains this X. So this is the first property of basis. So using this, so this is the motivation. We can define subbasis. So a subbasis is, if test for a topology is a collection of subsets of X whose union is X. Okay, so subbasis means it is some kind of partition, or not exactly partition because there can be non-empty intersection, but for example ABC, suppose this is a set, then this A, AB and this BC, this forms a subbasis. Okay, if we take those two things and denote it by S, this is a subbasis. Why? Because if you take union of those two things, union of AB, BC, this is actually X, right? Therefore it is a subbasis. Now why it is useful? This is useful because finite intersection of subbasis form a basis. Okay, so if we take finite intersection, so here the only intersection will be AB intersection BC, which is B. So from here we can extract a basis. So the intersection of those two things, it will be B, and there are other, that is intersection of only one element, that is AB itself. And similarly for BC we can take intersection of only this element, which is BC. So this form a basis, because what is the property of a basis? First property is for all those elements there should be an element containing this, so which is already satisfied by the property of subbasis, because subbasis is defined in such a way that their union will be the whole X. Therefore take any element, there must be an element of script S which contain that element. So first property of basis is already satisfied by S, so there is no issue. Now the second property is not, may not be satisfied by the basis, by the subbasis. Why? Because the intersection of those two things, the intersection is actually script, intersection is B, right? Yeah. So we have to take all possible finite intersections. Exactly. So intersection of all possible intersections. For example, there is only three possibility. So one is take intersection of those two things, which is this. One possibility is taking intersection of this only, which is AB, and similarly BC. So we can also take the intersection of over empty set, which will give me empty set, but I'm not taking because this is itself form a basis. This basis. So the okay, topology generated by the subbasis, it is actually by two steps. One step is create this script B, and now from script B you can create tau by the previous method, right? Take arbitrary union of those things, so that will give a topology, that is only ABC and empty set that will be included, right? So from this tau by the previous method, if we take union of those elements, then only empty will be included, and inclusion, another element will be ABC, that will be included, and those are already there. So this is top, and that will be called topology generated by a subbasis. First create a basis, and then from that basis we can create a topology tau. So we can define, we do not need a topology for a subbasis. Using subbasis is something smaller than a basis, so it is more easier to handle, right? It has less number of elements. So subbasis gives a way to count elements, because by definition we can take any collection of subsets. Yes, that will never form a topology, because empty and tau, empty and x we have not taken. Sorry, what? So we do not need a topology for a subbasis.
Hello. Hello.
Yes, the topology itself is a subbasis, right? Because you take union of all those elements, you will get X. You can take any collection of subset whose union. That will give me a topology. If we take any collection, no, I can't hear you, sorry. Pranja, can you talk? Can you speak?
Hello, sir. Am I audible to you?
Okay, sorry, there is a problem from my side. Now say again.
Hello, sir.
No, it is not audible.
So C is audible.
What is the problem?
Sandeep is audible.
Sorry, I don't know. There is some issue.
Sir, you can rejoin.
Okay. I can't hear. Sorry. Okay, let me try. Hello, can you hear me?
Yes, sir.
Hello.
Hello, sir.
Sorry, again there is some same issue. Everything is okay, but I can't hear. Okay, okay. Now I can't. Can you speak?
Hello.
Yes.
Yes, sir.
Okay, now I can't. I can.
Sir, you have defined subbasis as, sir, the collection of those subset of X such that union of those subset is the set X itself.
Yes.
So why do we need any topology to define the subbasis? Because
No,
we can take
we don't
any.
need any topology. We can define subbasis. So instead of S1, suppose take this subbasis. So take only A and take BC. So this in union of those two sets also is also ABC, right? So this is also a subbasis. But what will be a basis? So the basis script B, it will be A. So there is no other. So intersection is empty. So script B will be itself, right? From which we can generate script B because there is no intersection. It is already taken care. Now the topology generated by this. So take all union, all possible union. Now we can take.
Okay, so you want to say this S2 will be a sub-basis for this tau 2.
Yes, this
Okay.
exactly. That will give me something new topology.
So you should have written that this S script S is sub-basis for this tau 2.
Yes, exactly.
But you have written it in earlier statement that sub-basis script S for a topology. What that topology is, you are mentioning after that definition.
Okay, here we said that script S for a topology is a collection of subsets whose union is X. So this is a subbasis, this is another subbasis because their union forms the whole X. But that collection may not give the same topology. Here we can see that those two collection gives different topologies, right?
Okay, sir.
Okay.
Excuse me, sir.
Yeah.
So suppose I'm already given a topology.
Yes.
So suppose can you construct some B so that somehow it violates the second condition of the definition of the basis? I'm still confused about the second condition. So some explicit non-example might help to understand.
Okay. So let us try. Suppose the second condition is not holding, that is this one, right? Here, if we take this S1, which is AB and BC. Now the question is, if we assume this as a basis, then what will be a problem? So in this case, the first condition holds, right? That is, take any element. So we are considering the set X equal to ABC. So here the first condition is like this. So for any element A, there exists an element which is in S1. So the first condition of the basis is holding, right? For B there is something, for C there is something. But here the second condition is not holding. So the claim is this S1 cannot be a basis. So why not? That is, basis means their union should form a topology. But we will see that their union cannot be a topology. So what will be their union? So let us try to create all such union. So if we take unions, arbitrary unions of those elements, then one choice will be empty. Take union over empty set. Take union over this set only. Okay, union of this only. So it will give me AB itself. Take union of only this set, which is BC. Not union of everything, which will be ABC. Okay. Now the question, is it a topology? So if we give the name tau, is it a topology?
So it doesn't contain the singleton set B,
Yes.
which is why this contain.
Yeah.
Yes, sir. I think I got it.
So that for that condition, we actually need this property. That is, for any two thing, their intersection, whatever intersection is that. So take any element from that intersection. There should be some element containing this S1 and also contain that element X. Okay, so I am saying that if B1, B2, those two elements belongs to S1, and suppose X is in the intersection, so X belongs to B1 and B2 both, then there should exist B3 in that S1 such that this property holds. Okay, so this is the second property which defines a basis. If this property holds, then that will be a basis. If it does not hold, then we can see here this is not a basis, because if we assume this as a basis, then we can see that that will never generate a topology. Means in this case, it is not
So,
generated.
sir, so basically, sir, sir, we, we want to find a collection which whose arbitrary union can generate a topology.
Yes, exactly. Basis is like that, and subbasis is something more interesting, because in this case we are not allowing arbitrary union, we are also allowing finite intersection. So you can easily find any subbasis, right? So take
Yes,
any
sir.
set X, just make some choices such that their union forms X. But
Okay.
for basis it is slightly difficult, because you also need to see that condition, that is, this condition should also hold. Not only their union is X, but another additional condition is there. So subbasis means, basis means it satisfies the first property, that is, it satisfies the defining property of subbasis plus this additional condition. Okay, so basis, roughly, basis means subbasis condition plus this second property.
Union.
Not union. So it is saying if B1 B2 belong to this script B.
Okay, the finite intersection.
Not finite intersection. Actually, this script B is given by finite intersection of that script S. Is it clear?
Yes, sir.
Okay. So that is the whole story of subbasis and basis. Now let us solve some exercise. So here X is a set ABC, and two topologies given, tau 1 and tau 2. So the question is, smallest topology containing tau 1 tau 2, and find the largest topology which is contained in this tau 1 tau 2. So what will be the smallest topology containing tau 1 tau 2?
It's a discrete topology.
Indiscrete.
Indiscrete means it is empty and the whole thing. This is called indiscrete topology. and discrete means it has everything, it is just the power set. So let us see this. So smallest topology containing tau 1 tau 2, smallest topology, let me denote it by tau, containing tau 1 comma tau 2, let the smallest topology be tau. Okay.
Sir, I can tell you, sir.
Yes.
Sir, sir, empty set X, singleton A, singleton AB, sir, singleton B, BC, sir.
Yeah. So let us see. So tau 1 tau 2 both, that is tau 1 is a subset of tau, tau 2 is also subset of tau. Okay, that is the first property. So that means this empty set, all those things, so their union should also belongs to tau, right? So what is the union? Union is empty will be there, X is already there, X, and A is in the tau 1, B is in the tau 2, so AB, and AB is also there, and another one is BC, right? Now the problem is that union may not form a topology. As you can see that union of those two things, sorry, in this case the union,
Sir, it is forming a topology.
okay, it is forming a topology. In this case, here it is a topology, but in general that may not form a topology. So let us change a slide a bit. So instead of just, we can just remove this B. Okay, sorry, in this case then it will not be okay, it is a topology.
Sir, you can form a
Yeah.
next example.
Yeah, so we can remove B, so it is again a topology. Suppose this is the question now, therefore B will be not there, right? So here you can see that union always may not be a topology because intersection of those two things will be B, which is not present here, so it is not a topology. Okay, so can you generate a topology using that? You can always generate, right? Because this is a subbasis, and from using a subbasis you can always generate a topology. Yeah, just take finite intersection, form a basis, and take arbitrary union. Yeah. So first, therefore, the, so this is the subbasis. The subbasis. So let me denote it by S. Generates. What will be the generated thing? It will generates the topology. So first step will be take finite intersection. So what are all possible of possibilities? What are all those options? So first take intersection over those elements only. So we'll get the same thing, BC. So intersection means we are picking only single things, right? Now we can take intersection of those two things, which will give me empty. So intersection of something which is already content, it will give me the smaller thing, right? So we will not take those kind of intersection because it will not give me something new. So something new, the only possibility occurs this intersection, right? It has something distinct. So AB, BC, and the only different element we'll get will be B itself. So finite intersection, and now we will take arbitrary union. But we can see that this step is not needed. Why? Because it is already a base, it is already a topology. So from this subbasis we are getting a basis, but the thing is that this basis itself a topology. So whatever we will get is the same thing, we'll get the same thing. Okay, so the subbasis script S generate this topology. Okay, so from this example it is clear that the smallest topology which contains both tau 1 tau 2, it is the it is the topology generated by this union. So take this union as a subbasis and generates the topology. Generate the topology. Is it clear?
Yes, sir.
Okay. Now the question is something different. Now find the largest topology contained in tau 1 tau 2. So again, let us assume something. Topology generated by subbasis, yes, topology generated by a basis or subbasis will be unique. Yeah. So let tau dash be the largest topology contained in tau 1 and tau 2. Okay, nice. So if we assume that, then tau dash contained in tau 1 and tau dash also contained in tau 2, right? So that is equivalent to saying tau dash contained in both tau 1 tau 2, right? So let us find the intersection. So can you tell me what will be the intersection of those two things?
Sir, in discrete topology, empty
Yeah.
set X.
So here empty and X, those two are there in both tau 1 tau 2, right? So we just remove all other things. Okay. So the intersection is the empty set and X. So now can you say what is the maximum, what is the largest topology contained in this tau 1 tau 2 intersection tau 2? This is itself, right? Because it is a topology. Since tau 1 intersection tau 2 itself forms a topology, therefore the largest topology contained in tau 1 tau 2 is the intersection. And this story goes for arbitrary sets also. So instead of tau 1 tau 2, if any finite collection is given, the same story holds. Okay, not only finite, for arbitrary collection.
Sir,
Yes.
sir, if we have to find the largest topology such that which is contained in tau 1 and tau 2, in this case we have to always find intersection, and intersection of two topologies is always a topology.
Exactly.
So we do not need to do anything.
Yeah, exactly. So here is the same thing. That is, we are trying to find this tau dash, but the thing is easy here because tau 1 intersection tau 2 itself forms a topology. So we can take tau dash as tau 1 intersection tau 2. Okay. Earlier day we have seen that intersection forms a topology, but union may not form a topology. In the example, we can see that union is not a topology. So we can take it as a subbasis and generate a topology using that. Is it clear?
Yes, sir.
Okay. So here is the next question. Here the usual topology script f on real number r. So we need to compare those two topology. So one topology is usual topology. It is written as script f, and another topology is lower limit topology. So let us say what is lower limit topology. Lower limit topology. So instead of lower limit, first recall what is usual topology on A. Usual topology on R. So what is usual topology? Again, it is actually metric space. Exactly. So tau, it is defined as, let me denote it by the script f, which is already given. It is collection of all those open sets a comma b such that a is strictly less than b, and both a comma b are element of R. Okay. So this is basis for this script a, and this usual topology script f is the topology generated by this b. That is, take arbitrary intersection and take arbitrary union of those two. For example, if we take arbitrary union of this kind of element, a comma b and a comma b plus 1, and we increase the second one, a comma b plus n tends to infinity, that union will give me a comma infinity. So that is also open in this usual topology. Okay. So those are example. And lower limit topology, again it is given by this basis. So instead of b, let us denote it by b dash, and this, or maybe b0. So lower limit, there should be some limiting process. Lower limit means replace this a by closed a. Okay. So again the same thing, a less than b, both are real number. So the topology tau generated by this b0, this is called, we can rewrite as this. Here this is the notation. So that give me lower limit topology. Okay. So we need to compare which is course. The question is, usual topology script f is not cursor. So f is not cursor, then this tau. Okay, this is the question. So maybe this, I am writing in different notations, so let us be uniform. Okay. So this is the thing, we need to see if this is true or not. So how do we compare two topologies in terms of basis?
So this should be subset of the other one.
It is not strictly like that. So let us see if this is true or not. Let us check if script f is strictly smaller than script tau or not. Okay, to check. Okay, let us first check this. So script f is coarser than tau. That actually means the corresponding basis. So what is the criteria? If and only if criteria.
So if we take any element of
Yes,
basis of f,
any basis element from this script f,
yes,
that will be open in script tau. Okay, so this is if and only if for any b belongs to this basis from script f, sorry, b belongs to this script b, there exist, and x belongs to b, there exist b dash from this new thing b0 such that x belongs to b dash
set
content.
of b.
So is it true or not? We'll check if it is true or not. So take a basis, so replace this b by this type of element, right? This b will look like this interval, so we can denote it by ab. So for any ab, and take any element, for example take x belongs to this ab, can we find some element from this ab which lies in between this x and ab? Can we find some element like this?
Close interval x, open b.
Exactly. So yes, there exists x comma b which is contained in a, right? So this criteria holds, star holds. Since star holds, this will imply usual topology is coarser than lower limit topology. But it says the opposite. That is, it says that script f is not less equal to script tau. Right? So it says opposite, therefore the statement is false. Is it clear?
Yes.
Okay. So again, let us just recall what we have done. So we are checking that if this topology is coarser than this tau. So the easier way to check in terms of basis. Okay. So we can compare those two bases. So how do we compare? Take any element from the lower thing, that is this script b. We need to see that this is open in this tau. Okay, that how do we check this property? Take any element x belongs to b, and then we need to see this criteria holds. Okay, take any element from this basis and any arbitrary element from this b, this open set, this basis element, we need to see there should exist some b dash, then that will be also an open set here, right? That is the property how you can say it. Just see that this element actually element of this basis b0. So this is our B dash. This is the element B dash. And B dash satisfies this property. Okay. So in this question, we need to see which are correct or not. Incorrect. So first one says indiscrete topology is coarser than other topology. Any other topology defined on the same set. So indiscrete topology means empty and X. So any topology means it is a subset of power set satisfying some property closed under finite intersection and arbitrary union. And topology also satisfy the first property is empty and X belongs to tau, right? Therefore, any arbitrary topology must contain this empty and X. By definition, this is true. And similarly, again, by definition, topology is a subset of power set. So tau containing Px. And Px actually discrete topology, right? Power set has everything. This is discrete topology, this is indiscrete. Therefore, indiscrete is always coarser. This less equal to means this is less equal to and subset, whatever we say. This means this is coarser. Okay, and Px is finer. So here discrete topology may be coarser than the topology define the same set. That is not correct, right? So this is incorrect. B is incorrect. But A is correct. So we need to determine which are incorrect. Therefore, only B is incorrect. Here, maybe this is 1, this is actually 2. 2 is only incorrect. Okay? Because discrete topology always finest. The finest topology on any arbitrary set, whatever set you give me. Again, here we need to compare those three topologies. So, can you compare those two topologies? Okay, Sandeep, you know. So, compare means if something is contained in another, can you can you compare those T1 and T2? Is T1 contained in T2 or T2 contained in T1? So you can see. Yes, please go ahead. Yes. So can you write T2 contained in T1?
No, sir.
No, because there is some B, but B is not there. Okay, so T2 and T1 you cannot compare. The same thing will hold for the opposite direction. There is some AB which is not present in T2. So T1 and T2 cannot be comparable. But can you compare other thing T2, T3?
No, sir.
So in this case, those T1, T2, T2, nothing can be comparable. So all those options are incorrect. Okay. None of the above is correct. Because we cannot compare T1, T2, T2, T1. Because we can see, for example, if we try to compare T2, T3, then we can see that B is there in T2, but B does not belongs to T3. Therefore, T2 cannot be contained in T3. The same story goes for the opposite. That is, we can see BC is there in T3, but BC does not belongs to T2. Therefore, T3 cannot contain in T2. Okay, the same. From all those observation, we can see none of the above is correct. We cannot compare T1, T2, T2, T3. Okay. Here, tau on real number, tau is a topology, lower upper limit topology on real number. Okay. So what is upper limit topology? Let me denote it by this notation. So it will look like A comma this upper closed. Okay. A less than B, and those are element from R. A, B both are element from R. So can you see if this is closed or not? Sorry, this is open or not? 4 comma infinity. Is it open?
No.
Sorry, this is not tau. This is the basis for tau. Means tau will be generated by this basis. So we need to take finite intersection, all possible finite intersection, and take not intersection because it is already a basis. We only need to take arbitrary union. So close 4 comma infinity, is it open set? Can you see if it is open or not? Let us forcefully assume that closed 4 comma infinity is open. If we assume like this, then we can see that 4 belongs to this 4 comma infinity. Now can you give me any member from this basis? Let me denote this basis by script B. So is there any element of script B which lies between those two things? That is, there exists some B such that 4 belongs to this B and also contained in 4 comma infinity. Is there any member of B? So there does not exist, right? Because whatever we take, there is something smaller. That is, if we at least we need to take 4 comma something, but means less than 4, which is not, which cannot be contained in 4 comma infinity. So therefore this is not open. 4 comma infinity is not open. Now what about open 4 comma infinity?
It's also not open for the same reason.
Okay. Now let us see if this is true or not. So can you see that 4 comma infinity, this can be okay. 4 comma infinity, there this can be written as 4 comma this closed n, an arbitrary union, means union over those natural number. Can you see? Oh, sorry, here. Okay. Yes, it is okay. So can you see that we can write 4 comma infinity as union of these elements?
Yeah.
So union of open set means open, therefore it is open. And other way is like this. So you can check by the same method. Take 4 comma infinity, take any element x belongs to 4 comma infinity, then take just that element. Maybe 4 comma x belongs to 4 comma this x plus 1, and this is also contained in 4 comma infinity. Sorry. Okay, so whatever you like, this is easier to check always because we don't need to create some formula like this. So you can see by using this, it is clear that 4 comma infinity is open, tau open set. So this is true. Now what about minus infinity comma 2? Can you see this is also open or not?
Yes, sir.
Open?
No.
Okay, your guess it is not open set.
No, it is open, sir.
Okay, you are saying it is open. So let us check. So again, we can create a formula like this. So take 2 minus 1 by n and take union over 1 to infinity. In previous day, we have seen that actually gives me the same minus infinity comma 2, right? If you just increase this n, you will get everything minus infinity to 2. So sorry, here there is a slight issue. Okay, instead of open 2 minus 1 by n, take close. So that will also give me this minus infinity comma 2. Now can you see this is open in tau? All those elements minus infinity comma this type of elements, those are open in tau. Therefore this is also open. Arbitrary union of open set is open. So this is how we can check.
One thing here, like all the open sets are of the form A B, right? Can we just say minus infinity to 2 minus 2 minus n? I mean, I understand his reasoning, but this left side, it belongs to n, right? And n is a specific. It has to be some n belong to n, but
Yes.
infinity.
Okay, so you are so in previous example, yes, similar to the previous example, you can check that minus infinity comma something. Okay, minus infinity comma some a, that is also open. It is similar to that previous one. Just increase this. So here we can write minus n comma a and vary this n. So instead of doing like this, we can directly check by the definition, right? So yes, so we want to check minus infinity to this is open or not. Open in tau. This is what we want to check. So we need to see that for any x, let x belongs to minus infinity comma 2, we need to see if there exists some element, some basis element which lies between those two things. Okay, so what will be the basis element? we can choose x minus 1 comma x itself like this. So x belongs to this, and this also contain in minus infinity comma 2. Is it clear?
Okay, so this arbitrary union, right? Like it can tend to infinity. Okay, sorry. Yeah.
Yeah.
Yes, you can. Yeah.
So if only finite is allowed, then we'll not get this kind of behavior. So that is why arbitrary union of open set is open. That condition must be there. Otherwise, we will get weird thing. Yes, Pranja.
Explain why the first one is not open again.
Which one? This?
Option A.
Yeah. So option A here you can see that. So what do we check? How do we check something is open or not? We try to see if for every element there should be some neighborhood inside this set, right? So neighborhood means basis. So the neighborhood terms are replaced by basis. So we check some basis element is there or not. Okay. So we have taken some element 4 here, 4 from this set. Now we see that 4 has no neighborhood, right? Whatever you choose from this basis set, is there something 4 which belongs to this and also this?
I'm still confused. Can you please explain this again?
Okay. So can you see 4 belongs to AB, some AB like this, and this is also contained in 4 comma infinity. Sorry, yes, this is what it is given. Can you see if it is?
Yes, sir. Yes, I think I see this. Yeah, I get it. I get why this one.
Yes. If 4 belongs to this AB, then this A must be something strictly lesser than 4, right? So A will take this form 4 minus epsilon. But whatever you choose, some B, but whatever you choose 4 minus epsilon, then you can see that 4 minus between 4 minus epsilon and 4 there are lots of numbers, uncountably many numbers, right?
Yes, sir. It
Yeah,
makes sense.
you can take 4 minus epsilon by 2, which is also there. So that cannot contain in 4 comma infinity.
Okay,
So
sir.
that is not possible. Impossible. Or contradiction, whatever you say. So okay, so I have given 2 methods to check something is open or not. So okay, so this is how you can check something is open or not. This is more easier. You don't need to create some formula like this. You just check if there is some neighborhood or not. Neighborhood which contains that element and containing that set. This is simply just a real analysis. How do we check something is open? A set is open or not? We just see if there exists some neighborhood which containing that set. This is how do we check.
See, but in topology, right, like the concept of open set is like it's completely different, right? Like it doesn't, even finite sets can be open in that particular topology.
Yeah.
So can you sort of expand on this, like on this conceptual difference? Because in real analysis, we are used to that distance. We have a metric. We can always find an open ball, and all points are interior. Many definitions are there.
Yeah. So in real analysis, we see that a finite set cannot be open in real analysis because open set it must contain some interval. So finite set cannot be open. But in metric space, we see that this is not true. For example, discrete metric, in discrete metric, finite set is also allowed to be open, right?
Yes.
So that concept extends further. So instead of those kind of distance, we don't need those kind of distance or those kind of. So real number has lots of structure, real number or Rn, but instead of having those many structure, using only set theory, we can study continuity and those kind of properties. So there is, so basis gives the idea of neighborhood. So element of basis that behaves as a neighborhood. So those kind of, yes. So we can study continuity and those homeomorphism, those kind of properties, just
Without a metric.
without a metric, without having those many structure. There in metric space there is limitation because it has some structure, but here we don't have anything. We just define topology, means it is an abstract definition, and now we can relate with those real analysis or metric space definition.
One small foundational thing, it's something very basic. So this, when they say in a topology, an arbitrary union must exist in the topology itself. That union can be countable or uncountable, right? Like it need not. Is there any restriction on being it countable or uncountable?
No, there is no restriction. Here you can take any kind of. That's why I am saying arbitrary union, because you can take union over uncountable many objects.
But intersection has to be finite. Like
Yes,
intersection has to be finite, and it cannot even be countable.
Yes, intersection is strictly finite. You cannot take count.
Thank you.
So we have seen that this is also open, but now 1,2, is it open? Again, the same idea will hold, right? 1,2. Let us see if it is open or not. Okay. So if we take 1,2, then the question is, for any x belongs to 1,2, can we pick something like that? So just observe, we have seen that upper limit topology is coarser. Sorry, upper limit topology is finer than usual. So upper limit may be denoted by tau upper, that is finer than tau usual topology. Usual topology on real number, that is coarser than upper limit topology. It is just similar to whatever we have done for lower limit. Maybe here, yes. So that actually holds, that upper limit topology is finer. So whatever open set, whatever set is open in usual topology will be also open in upper, right? Because this is just a subset. So if something is open in usual topology, that will be also open in upper limit. Therefore, that is also open. Is it clear? This is more easier to check. So that is open in real number. This set also open in real number. This is also open in real number. So all those three are open in real number, which is usual topology. And usual topology is subset of. So if something is something belongs to tau usual, that will also belongs to tau upper. Is it clear?
Yes, sir.
Okay. And this is how we can directly check. Without using those kind of property, you can directly check if that is holding or not. So here question number 6. So two things is given. One is the class of all open equilateral triangle with one side. Means this means those kind of triangle. So one side is given, right? This is equilateral triangle. So all those interior point is there, but this side also presents. Okay, and the second one is the class of open square. That means it will look like those kind of thing in R2. Okay, so those are two classes. Now the question is which forms a basis for the usual topology on R2? Can you see if
Sir, second one.
yes? How do you check if something forms a usual topology?
Sir, for any element belongs to X, there exists some element in that collection such that X belongs to that element.
Yes. So B is a basis for tau. So how do we check this?
For all X belongs to capital X,
Yes.
there is some B
X
belongs
is the
to,
given set on which we are considering topology and basis. So for all X belongs to X with
there is some B belongs to script B.
for all X belongs to X, and means first one is for all U belongs to tau with X belongs to U, there exists some element, basis element, that is there exists some neighborhood such that X belongs to this neighborhood and this containing this U. So that is how we can check that script V produce the topology tau. So can we see that this square actually produces a topology which is same as usual topology? So we need to check this property, right? So the problem is here we need to see arbitrary element of tau, which is not easy to see, but we can also directly see that this forms a basis. Is it clear? This forms a basis. So first
Sir,
one is
what?
that yes. Is it clear that
Sir, we can use the definition of the basis only, na sir?
mm,
Just
No,
looking
any open set in arc square can be approximated by a union of these squares, right? Which is what we do in integration. Not along that idea we can take.
yes? So okay.
And since every open set, every open square, no matter how small, is belongs to this topology and
Yes.
their union. Therefore, any shape on R square, right? Any open shape on R square, yeah,
Yes,
like
exactly.
we can take a
So
limit. Yeah.
exactly. So suppose this U is open in usual topology R2. So what is the meaning of that? This means for any whatever point you choose, let X belongs to U, there exists an open ball B which contains that point X, right? This is open ball. So it is actually dotted region like this, right? Now you can see that for any open ball, there is, you can just take this inner square, right?
Yeah, this is what I had in mind. Yeah,
Exactly. So you can see that this property actually holds. So you have chosen an arbitrary open set U in R2. You can produce such that X belongs to U. Then you can produce this B. There exists this B such that X belongs to this B and X also belongs to that open set. This U.
but the problem here is like for an arbitrary curve or for an arbitrary open set, we have to do all that like proper epsilon delta, right, with these squares so that we
No,
get that.
we don't need. Why? Because we already know for arbitrary open set, this is open means there should exist some open ball. This is by definition
Okay, yeah.
metric. Now you only need to find this box inside this disk, which is
What he meant was when he write down the proof, right? Like
yes. So how do you
like,
get this square?
yeah.
This is the question, right? So this square you can always get because just take this circle of radius 1. Sorry, disk of radius 1. Suppose this is disk of radius 1. Now can you approximate it by this square inside the disk? So this is actually disk of radius 1. So what will be can you describe the square?
Yeah, root 2. That is root 2r.
It is?
And yes, there's a mapping. Yeah, for every ball that I can produce a square.
Yes,
with
it
radius,
is 1 by root 2.
This is
So
root 2 epsilon, like the side is root 2 epsilon.
yes, this square you can explicitly describe. So let me denote it by like this. So yeah, so it is actually it is minus 1 by root 2 comma 1 by root 2 times this, right?
Yeah. Thank you. I got the. Let's go ahead.
Yeah. So now for any square, just shift and shrink. You can find those kind of thing. Okay. So it means in my notation we can just shrink it by some n and just shift plus some a. That will give me this square. Okay. Now the second one, sorry. So this is a basis for usual topology, right? So the 2 is correct. So this is actually 1. This is 2. So 2 is basis. It is correct. Is a basis for usual topology on R2. Now what about the first one? So is it a basis? So the thing is,
Yes.
this will be a basis, but the question is, will it be a basis for this usual topology?
We use the same 1 plus that limit plus 1 by n, right? Argument on this same thing and produce an open set with that infinite union.
Yes,
yeah,
exactly. You can produce, but the thing, this topology will be finer, right? It is similar to that scenario. It will be like A comma B, this kind of scenario. So it is similar to that. That is this kind of generalization. AB belongs to R. So we have earlier seen that lower limit topology is finer, strictly finer. So I want to mean that this is strictly finer. So this topology generated by this thing will be bigger. So this cannot be open in R, right? So you can already see that this thing that can never be open in R2. in usual topology, is it open? The interior, you can see that it is also there, right? This one side is there. So this cannot be open, because if you take this point, then there is no open ball which contains this point and also containing this kind of filled triangle. Is it clear or not?
But if we use it, say A as 1 plus A plus infinite union of A 1 plus N, 1 minus N, so to speak.
Yes.
Then if I take the infinite union of that, then that should also be an open set in this thing, right? So if
you are taking infinite union of A minus 1 by N comma B.
Yeah.
But the problem is, if you take infinite union, then it will be closed A comma B. Sorry, A minus 1 by N.
Yeah, and all those things are in this.
Sorry.
Okay, the antecedent, it is not there in this set. Okay, there it was. Okay. So
What are you saying?
It is not there in this basis actually. Okay.
Yes.
Yeah, okay.
So this is open AB, sir.
Open AB. This will be open AB, because
Sir, what is usual topology?
sorry,
on
union
R2, sir?
means it is the bigger thing. Intersection. You need to take intersection to get closed AB. Yes. What are you saying?
Sir, what do you mean by usual topology on R2?
Okay, usual topology is same as metric topology or Euclidean topology.
So it is generated by open balls.
Yes, exactly. It is generated by open balls. So here we can see, for this point, there exists a neighborhood, that is basis element, which does not contain in this whole region.
So sir, when does a collection form the basis?
Yes.
When we already have basis. So is there any relation between two bases of a topology?
Two bases in a topology means, relation means we can always see if something is finer or coarser. Sometimes it happens that topology generated by those two bases are same. For example, here you can see that topology generated by this basis, actually it is same as topology generated by those open balls.
No, sir, I am asking that when two bases generate same topology.
Okay, that you can see by this kind of comparison result, right? So you first check tau b1 is coarser than tau b2, and similarly you can check the other way, and using those two, if two things holds, then that will be same. Those two topology will be same.
So also we can use the fact that if we can write elements of some basis as the union of the elements of basis of
Other element,
other
other
basis.
one. Yes, exactly. You can also try using that way.
That is what you have, sir, used here.
Yes. Here I am not using that,
No,
because
sir, you have used that every open ball can be, sir, written as the union of squares.
yes, we can say that exactly. So if for every open ball you can find some square which contain in that open ball. Okay. So you can see that this is actually a basis, but this is not a basis. Even those sets are not open. So first property will be that, right? If something is basis, means all elements should belongs to this term.
That means they should be open.
Yeah.
Elements of tau are said to be open, sir. Huh?
Yes. Elements of topology are said to be open sets. So this is not open actually. And those are not open in usual topology. Okay, so 1 is false and 2 is correct. Is it clear to all?
Sir, if we take any closed figure,
Yes,
then it will never form a basis for
exactly.
usual topology.
It cannot form a basis in usual topology
Yes, sir.
because there will be some boundary which will create problem.
Yes, sir.
So here A is closed under which topology? So what is closed? So given a topology tau,
Complement open.
yes, a set. So tau be a topology. We are considering some topology. Then in this topology, with respect to this topology, a set A is said to be closed if complement of A is open. So a closed set is defined by complement of open set. Okay. So the usual topology over R. Under usual topology, is it a closed set?
Yes, sir.
Yes, sir.
So it will be not a closed set. Why? Because you can see if A is closed, then complement of A should be open. So what is complement of this R minus A? It is like this: minus infinity comma 0, close 0, union, something like this. So it has some interval 1 by n plus 1, comma 1 by a. And there should be another union. So that will create the problem, this 0. Right? Those are open, but this 0 will create the problem. So another way you can see that this is not closed. Why? Because the limit, what is the limit point of 1 by n? Though I have not defined, but you already studied in real analysis that limit point, this limit of 1 by n is 0. But 0 does not belong to this set, right?
Yes, sir. Makes sense.
So a complement is not open.
So how did you come up with the definition 1 by n plus 1, 1 by n? It consists only of the points 1 by n.
Yes. So I am just removing 1 by n from the real line. This is the real line. I am just removing this 1, half, and so on. It is 1/3, 1/4.
Ah, okay. Now we get it.
So we'll get. Okay. So you can just see that point 0 belongs to this point, but 0 has no neighborhood which contain in a complement. So the usual topology is, this is not closed under usual topology. So what about co-countable topology?
It is open.
Yes. So how do we define an open set in co-countable topology? In co-countable topology, open set are either phi, empty set, or open set is complement of countable set, right? Complement of that set, that is here R minus that set. Is it clear?
Yes, sir.
So 1 by n, can you see that what? So open is complement of countable, therefore closed will be open complement of open. And complement of open means either this is countable, and there is another possibility which is whole. That is, open is not always like this. Open has two choice, either empty set or complement of countable. So it has also two choice, closed set. Either so complement of empty means whole set or a countable set. So can you see A is countable or not?
Yeah, it's countable. So
It is countable, therefore it will be a closed set. A is closed with respect to port countable topology. Now what about cofinite topology?
it's
So yes, again using the same analogy, in cofinite topology, closed sets are either, there are two choices of closed set. It is either finite set or it is the whole set, right? So is it finite set?
Mm.
1 by n? This is not a finite set, right? It has infinitely many elements. Therefore, this is not actually closed in cofinite. Okay? So only C is the correct answer. Now, I have two questions. Let us solve these two questions. It is so X is this set. It has 5 elements. Now, can you find a subbasis of this X which does not contain any singleton element? So we need to find a basis for discrete, a subbasis for discrete topology. So one subbasis will be like this. Take those singleton set. Take A, take B, take C, D, E. But in this question, it is not allowed that you cannot pick those singleton set. So subbasis means what? Its union should be the whole set X, so it satisfies that property, and it also creates discrete topology. Because take finite intersection, take arbitrary union, you get the whole power set. But this is not allowed here. Not allowed in this case. So what will be the other choice? Can you suggest me? So take the subbasis like this. So instead of A, we can pick the pair AB. So AB, BC, CD, DE, and EA. Now can you see this will also form a topology? So union is whole X. Union of those things is actually X. So it is a subbasis. Now can you see this forms discrete topology?
yes, sir.
So if you take the intersection of those two things will give me B. These two things will give me C. This is D, E, and similarly intersection of those two will give me A. So we get all those singleton element, right? Now take those union, we'll get the whole power set. Is it clear?
Yes, sir.
Okay. So this is the last question, but this is just the definition. So I am not. And this is just a property you can look at. So let us stop here. Any question? Is there any question?
I don't have any questions.
Yes, go ahead.
No, I said I don't have any
Okay,
questions.
okay. Good. So let's stop. And thank you for being there.
One thing, like which book gives many examples like this, like so many examples are discussed, like any book that gives because most of the books are very like just theorem proof like.
Yes, that's a problem. There is a nice book. Someone there in that book there are lots of examples, but you need to solve those examples by. So I have forgotten. So I'll suggest the name in the next class. Okay. Probably Francis. Someone. Topology Illustrated or something, not like that. But that book is nice. I will suggest the name.
Okay. So these slides will be up sometime, or like you will upload only the talk entire recording, or like the slides will.
Yes, I upload the entire recording as well. I also upload the notes also. This kind of notes.
Yeah. Okay. Thank you.
Okay. Thank you.